All right, calc folks, we've got some notes on slope fields. So this is sort of a follow-up to differential equations and solving them, which we've been doing in class. And slope fields are just a way to visualize the family of functions that differential equations provide us. So if you remember back to class, there are certain differential equations that have multiple solutions, like a family of functions, and slope fields can really help us visualize that. So let's start here with this example, dy dx equals 2x. So that's the derivative of y with respect to x is going to be equal to 2x. So there's a whole family of functions that can represent that. But we're going to go about plotting some points, the slope of this toothpick tangent. I'll explain that later, but let's go through that real quickly. So when x is equal to -2, if I plug in -2 up here, I'll know that my toothpick tangent is going to be -4. So for all these ones with a -2, I'm just going to put in -4 there. And then for -1, it'll be -2. So all these can be -2. Then we've got x is equal to 0, so that'll zero out. We've got slope of 0. You can start to see a pattern, 2, 2, 2, 4, 4, and 4. So let's plot these. So when I'm up here in this, this quadrant, I'm going to have x values that are negative and y values that are positive. But my x values are sort of the only important ones. So I've got an x value of -2 and +2, so I'll get a pretty negative slope. And you can sort of follow these x lines because x is the only thing that really affects the slope of our tangent line because it's 2 times x. So when x is negative, we get a 2x multiplier, so it's a reasonably negative slope. When x is slightly less, our slope is probably slightly flatter. So do something like that. Fill these on in. And this is just a rough estimate. And this is what I mean by these toothpick tangents. Just you're drawing tiny little tangent lines. As we get closer to our y-axis, it'll get even flatter and flatter. And again, these are just estimates and they're a little messy. And then when our x is equal to 0, we've got a flat slope. No slope. Slope of 0. And then kind of the opposite. So we start flat, get a little steeper, flat, steeper and steeper. This is looking a little redundant. This is where I wish I had some video editing skills. So you can start to see our slope field taking shape here. And so all this is representing is kind of our potential options. We need to follow the directions of our toothpick tangent to draw a curve. So I'm going to draw one that follows my toothpick tangent, that kind of obeys the rules of the road here. So I get something that looks like a parabola. And it says how many curves are possible here. Now it's an infinite number. And how do we know that? Because I can still follow our slope field here. And if the kind of graphical representation doesn't cut it for you, let's go back to our initial equation, dy dx is our original differential equation, equals 2x. So let's kind of do this in reverse. So what this is the derivative of a function. So I'm going to say my original function, y, was x squared plus 5. Does that satisfy this equation? dy dx, yep, 2x. Okay, let's try y, let's call that y1, let's try y2. Let's try a different one, x squared plus 1573.2. Surprise, surprise, 2x. So we've got this plus c here, and we can move up and down in this direction, and we're still obeying this slope field. So we've got this whole family of functions, y1, y2, all into infinity, that satisfy this slope field. So the slope field can help us visualize what our family of functions will look like. So let's do an example here. Start with the first one. So we've got dy dx is equal to negative y. So all that really matters here is our y values. So start with some easy ones. When y is equal to 0, our toothpick tangents are also going to be 0. So we've got a flat line here. And then as y is positive, our slope will be negative. So all of these will be reasonably negative because we've got a positive y value. And then as it gets more positive, it'll get steeper. So steeper and steeper up here. And then sort of the reverse down here. We'll have a positive slope when our y's are negative. And then it'll get even steeper when our y's are more negative. So this one's a little more interesting. But we've got this question here that says sketch your particular solution to dy dx equals negative y that passes through this point. So this is not general anymore. This is a very specific solution. So this is linking back to what we were doing in class of, does this solution represent this differential equation? Is this specific solution within our family of solutions? And so let's try to plot this specific solution. It's going through x of 0 and a y of negative 1, so something like this. So that's our specific solution to a family of functions that our slope field is representing. I will let y'all try this one. Maybe there'll be some Edpuzzle questions on that. And we will move on to this, where we've been given a slope field. So there's some differential equation, dy dx, floating out there that produced this, where, say, the slope of 3, or I don't know, 0.1 comma 3, or 0.1 comma anything, a small x value is going to produce a really steep positive slope. So there's something like that. So let's see. If I've got a really small x value for e to the x, e to the 0.01, is that going to cause a really steep positive slope? Well, probably not. Probably be pretty small. Same with 0.01 squared. Probably can write both of those off. Now what about sine of x? Well, we don't really see any kind of cyclical fashion going on here, so can write that one off as well. And boom, there we go, ln of x. So that's just, again, log base e, as we remember. Back to pre-calc. So this is going to be a slope field for ln of x, and if we remember what those look like, they do generally follow this slope field, unsurprisingly. So our answer is C there. Let's get on to this last one before this video gets too long, which gives us a differential equation, and we want to find a particular solution that satisfies this. So f of x, so we've got a point 3, and it produces the y 4, and we want an equation of the line tangent to this 3 comma 4 at x equals, that should be 3.1. Use this line, or no, sorry, I had that right. So at x equals 3, use this line to approximate the f of 3.1. So we need to find a line tangent to x equals 3, and then that can help us get our f of 3.1. So how are we going to get our tangent line? So we're probably going to want something that's in our point slope form. So we've got our our x1 and our y1 points. All we need is our slope. So how can we find the slope at a specific point? Well, we've been given a really helpful differential equation which says our slope at a point is actually just equal to x over y. We have our x and we have our y, so we're kind of done. Y minus 4, because that's our y1 point, equals 3 over 4 as specified by our differential equation, x minus x1, which is 3. So that's our point slope form. Now it says use this line to approximate f of 3.1, or another way to say that is what's our y value when x is equal to 3.1, given I know the slope at this specific point, that's why we're approximating. The slope at 3, 4 is exactly 3/4, but we're going to use this line as an approximation for something that's pretty close to 3, 4, which is x is equal to 3.1, and we need to find the y value. So all we have to do is plug in our x value, 3.1 minus 3. I'm kind of writing backwards here. And all we have to do is solve for y. So kind of move our 4 over. That's 3/4, 3.1 minus 3 plus 4. And that will give us our y value of, already calculated this one, what do we got? Y is equal to 4.075. So we have a point 3.1, 4.075. And I want to stress that this is an estimate, because we used this differential equation which produced a slope for the 0.34. The 0.34 has an exact slope of 3/4, and we are using that to estimate the slope, and we're using that to estimate the actual value, the y value of a point at 3.1. Now it's not exactly there because that is not exactly our slope at 3.1, because we did not use the differential equation specifically. So I just want to reiterate that that's an estimate. We're using our slope at an adjacent point to find where our y value is. All right, that is all I got. Hopefully this plus the Edpuzzle questions have been helpful, and I will see you back in class for more on this.